Okay, so in the previous sections we have defined the language modeling problem, and we have introduced this very important class of models, trigram models for language modeling. Very soon we will describe estimation methods that alleviate the problems with sparse data that I described in the previous section. But before I get to estimation, I want to describe how we can evaluate the effectiveness of different language models. And to do this, we will describe a very important measure called perplexity, which is widely used as a measure of the performance of a language model. So now let's define perplexity. So as I said before, we've assumed in the language modeling problem that we have some training data consisting of many sentences in the language in which we are interested. In addition, we're going to assume that we have some test data sentences. Use little m to refer to the number of sentences. So we have S1, S2, S3, up to SM, where each of these is a sentence in the language. So S1, for example, might be the dog laughs, stop. It could be any sentence. Critically, while we will assume that the parameters of the language model are estimated on the training examples, we'll assume that the test data is a separate, held-out set of examples which were not used in estimation of the parameters. So the test data are new, unseen examples. Given the test data, it's natural to look at the probability that our language model assigns to those test data sentences. So here I have a product from I equals 1 to m, p of si, where this p is itself some product of terms. For example, the given star star times q of dog given star there times and so on and so on. This function p is a function of our parameters. Now, a good language model, intuitively, should assign as high probability as possible to these test data sentences. You can think of this value as being a measure of how well the language model predicts these test data sentences. It's actually slightly more convenient to, instead of looking at this product, we look at the log of this product. So if I take the log, by the usual rules of logs of products, I end up with the following, which is a sum from I equals 1 to m of the log probability under the language model of sentence si. And again, the higher this quantity, this log probability, the better our language model is as a model of these test data sentences. So this would actually be a perfectly good measure of the quality of a language model, but we're going to transform this quantity in a couple more steps, which will be convenient, which will turn out to be convenient. And so first I'm going to define this value L, and this is just dividing this log probability by capital M, where M is the total number of words in the test data. So this can now be interpreted as the average log probability word by word in my test data. And it's basically a quantity which is now normalized with respect to the length of the test data sentences. So it, in some sense, is now stable with respect to the length of the test examples. This log, by the way, is going to be defined as log base 2. And the perplexity is now defined as 2 to the minus L. So I take this log probability, I divide by the number of words, and then I raise this 2 to the minus L. One important point about perplexity is the higher this quantity is, the log probability, the better the fit of the model to the test examples. And that means, because I have 2 to the minus L here, lower quantities of perplexity are better than higher quantities. The lower the value for the perplexity, the better the language model is as a fit to our test data examples. So this is the standard measure of quality of a language model. Let's talk a little bit more about this, giving some perplexity values and also talking a little bit more about some important intuition behind perplexity. So one thought experiment is the following. Say we have some vocabulary V as before, and I define capital N to be the size of V plus 1. And let's say I have the dumbest possible language model where each parameter is just 1 over capital N. So remember, W in this case can be any value in V, or it can be the stop symbol. And this language model simply assigns the uniform distribution over all possible words at each position. So it completely ignores the previous two words, and in addition, it has no model of the relative frequency of different words, the fact that this word in English might be more frequent than that word in English. It's, as I said, the dumbest possible language model you could think of. It's easy enough to go through the equations on the slide I showed you previously and recover the fact that L in this case is log 1 over n, and the perplexity is 2 to the minus L again. And the perplexity in this case comes out as simply n, basically the vocabulary size plus 1. So you can think of the perplexity as a measure, in a sense, of the effective vocabulary size. Under this dumbest possible model, we simply get the vocabulary size, and under statistical models, we can improve upon this because some words are more frequent than others, and we condition on the context, and so on and so on. Here, to just give a little bit more intuition, are some values for perplexity taken from a paper by Joshua Goodman called A Bit of Progress in Language Modeling. Here he considered a setting where the vocabulary size was 50,000, and I believe it was newspaper text. And here are some numbers. So for a trigram model, which is just as we had defined before, we condition each word on the previous two words, and with appropriate estimation techniques, which we'll describe a little later in this lecture, the perplexity came out at 74. Notice that is vastly smaller than the vocabulary size 50,000. So we've done much, much better than simply predicting a uniform distribution over each word in turn in the sequence. You can see that this statistical information has given great benefits in terms of perplexity. Goodman also looked at other models. So one is a bigram model. A bigram model is very similar to a trigram model, but at each point we condition only on the previous word, xi minus 1. So this is essentially a first-order Markov process. Remember this, a trigram model, is a second-order Markov process. So we're conditioning on less information, just the previous word. And of course we lose some statistical power there, and the perplexity does go up a bit to about 137, which is a pretty significant change from 74. He also looked at unigram models. In this case, the probability for any sentence is a product of terms. I have qxi, which actually completely ignores the context. And so we just have a parameter qxi for each possible word. And so we're predicting each word, ignoring the previous two words. This model will have the ability to model the differences and frequencies of different words, but will have no ability to model context. The perplexity in this case was close to 1,000. So you'll notice that this is really dramatically larger than the value for a trigram model. We've certainly got a lot of benefit out of conditioning on the previous two words. It's still rather better than 50,000, though, the vocabulary size. So in short, trigram language models give considerable improvements over just a uniform distribution over the vocabulary, or unigram, or bigram models. You can, of course, go further to what are called 4-gram models, which condition on the previous three words, or 5-gram models, and you will, given enough training data, see some improvements if you do that. But trigrams are getting pretty close to the state of the art for this problem. I just want to finish this segment with a little bit about some history behind the idea of language models. And a critical reference is due to Shannon. And this is really one of the earliest pieces of work on this problem. This is from 1951. Claude Shannon was really a huge figure in information theory, huge early figure in information theory. And he actually did experiments where he looked at basically bigram, trigram language models and so on, building as we did from Markov processes as a starting point. And it's a very interesting paper. It's well worth reading. And amongst other things, it actually measures how well humans perform as language models. So it actually looks at how well humans will predict the next word or maybe the next letter in a text. Turns out that humans really perform quite well in this problem, probably better than the trigram models I've just described to you. Actually, probably better than any language model that we've come up with at this point. So that's one very early piece of research. Another very interesting reference is due to Chomsky. So syntactic structures is a hugely influential book in modern linguistics. And it's a wonderful book. I highly recommend it if you're interested in language. And here he has a detailed argument about the role of probability and statistics in linguistics, specifically its role in grammaticality, predicting whether a sentence is grammatical or not. So this is a very involved argument. It has provoked a lot of discussion. I won't get into it. But he has arguments for why probability really doesn't have much to do with grammaticality. And it's a very interesting argument. As I said, I won't get into the details. And as I said, and he, I think, is, it's not entirely clear, but I think he's very much has Shannon's experiments on Markov processes for language in mind. There are clear arguments that these processes fail to capture the kind of longer distance dependencies which are a critical part of language. And as I said, later in the course we'll see more powerful models, such as context-free grammars, which begin to get at more interesting long-range dependencies. Having said that, as I said before, trigram language models are tremendously useful in practice and in applications such as speech recognition and machine translation and so on. They play a critical role, and they've been very hard to improve upon.